back there. We're starting back up. So we're going to finish knowledge acquisition and knowledge-based systems, and then we're going to move on to Bayes networks and probability and statistics, but we're not going to do probability and statistics. We're just going to examine how that works with the field of AI and how the crossover is associated. So we left off on slide 50. There's about 20 slides left on this, this PowerPoint. Gets into the concept of knowledge acquisition. So it's an architectural principle that we're working with, and the principle is that knowledge is power, hopefully, and that knowledge is often inexact and incomplete. So what we're going to try and do is represent knowledge, which is what knowledge acquisition is all about. So we know, as an example, the weather system is knowledge acquisition, because we don't know that this concept of there being precipitation and this concept of there being rain, you know, that we can look at a weather report, we can see it's going to rain. Actually, it was supposed to rain today. There was like a 20% chance or 30% last night, but today is a 0%, which means that they've changed it, they've updated it. The knowledge acquisition has changed since yesterday and today, and now we have new knowledge that's going to say, hey, it's not going to rain today. But that's what's called knowledge in terms of the architectural principle of what it is we're mining or what it is we're using as a knowledge base for our expert system. So it's often poorly specified. It's often not very structured. Amateurs become experts slowly in terms of the process. Expert systems must be flexible to work with all sorts of knowledge, and it must be transparent, and so we have a separate inference engine and knowledge base that's used to make use of the system and make systems easy to modify, hopefully. So knowledge architectures in terms of the principles fall into these categories and these characteristics. So we use the ununiform fact representation. So now I'm going to wake you guys up and get you to all stop talking. I'm going to say, on the final exam, oh, it works, see? It's beauty, it just works. All you have to do is say, and that's what you missed on the final exam. And then I got everybody's attention. On the final exam, I'm going to ask you a question about knowledge representation. Hint, hint, it's coming out of this lecture. And the question might ask you, what are some examples of knowledge representation? Well, a fact is a representation. It's sitting right here. Use uniform fact representation. Reduces the number of rules required and limits the combination of the explosion. Knowledge is represented in the terms of facts. Knowledge is rules. Knowledge is information. Knowledge is data that's being captured in a database. Knowledge is anything for which we can put a label on it, call it knowledge, and it's being represented in some form in which we can use in an expert system or in a logical deduction system, or in anything related to the application of it. So that's going to be helpful to know for the final exam for tomorrow. Keep the inference engine simple, makes the knowledge acquisition and truth maintenance easier. If the inference engine is only checking, for example, we'll talk about a weather system again. If the weather system is only looking at the precipitation and whatever leads into precipitation, and if that's the only rule that's going to determine whether or not it's going to rain tomorrow, then we're going to use that. And that's a simple, very simple inference engine. It's only one rule. We're probably going to use a little bit more than that, and they use a little bit more. But what they normally show the user is the percent of precipitation, because that's usually an indication. It's one of the main indications. So if we keep it simple, then the knowledge itself is actually more adaptable and works better. Works more better, so. So we can exploit the redundancy. Can help overcome problems due to inexact or uncertain reasoning. So if we keep things non-redundant, if we keep things redundant, in fact, exploiting redundancy is referring to what we get in databases. So going back to Oracle from last week, if you were in that class, and I talked about controlled redundancy, and I talked about how redundancy could be good and bad. It's the same thing actually with artificial intelligence. It's exploiting the redundancy so we can make the connections just the same way as a key is controlled redundancy in a database, a primary key and a foreign key. That's redundant. The piece of information is shown twice in the database, two different database tables. But we exploit it by making it into a concept of a connection or a relationship between those two tables Well, you're doing the same thing with artificial intelligence in terms of that database. So the knowledge representation might be in the form of a database, a classical database, or it may be in an in-classical database. A lot of knowledge is actually represented in spreadsheets, in text files, in survey outcomes, survey results. This is the raw data, and it's not necessarily knowledge. Data is not equal to knowledge. Data plus inference engine makes the knowledge. So the idea of the artificial intelligence is to create knowledge from the data, and so the inference engine is actually doing it. So they both work together. So the criteria for selecting a problem that's going to work this way. So this is something that you can use for your CSLO essay in terms of selecting a problem that you're going to try and solve, because you can actually take an artificial intelligence expert system or knowledge acquisition or knowledge representation approach to that essay if you'd like. And if you're doing that, what you're going to do is select something that's recognized as a problem where there's some experts that exist. For example, expert medical people diagnose conditions. They're doctors. They're called doctors. Dentists clean teeth and find cavities and stuff. So you can have an expert that exists, and what you're trying to do is represent that expert in the artificial intelligence system. So experts do better than amateurs, hopefully. And the expert needs significant time to solve the problem. And if it's not a significantly complex problem and it doesn't take very much time, it makes no sense to write a program for it. It's kind of like sometimes, you know, when you think of these applications. I'm waiting to see if these guys are going to be quiet. Are you done? Thank you. I was just waiting for you guys to finish because I didn't feel like competing with you anymore. All right. Back to the lecture, now that I've got your fullest attention. So, we have experts. You can talk, just don't make it louder than me. So we can have experts that need significant time to solve the problem. If it's a trivial problem, there's absolutely no need to formalize it in an expert system. So we also could have problems of cognitive type tasks, which take cognitive reasoning. We can also have problems of other types of tasks, like, say, for example, artistic tasks. There's programs out there that do scanning for you, that'll take an image and scan it in and do artificial recognition of the image and do pattern matching to fill in pieces of the image that might not scan well, do text recognition, do all sorts of different things. That's an artificial kind of knowledge representation where it's filling in knowledge artificially that a human's not doing. So that also falls into the same category. And skills can routinely be taught to neophytes or beginners, meaning that you have to be able, and when you're creating the problem for the solution, it has to be something you can teach somebody to do. Like, for example, the medical thing, you know, you have to have a person who's operating the program who can take a blood pressure or who can take a pulse or something, so you can put the information into the diagnostic system so that you can analyze it correctly. If you can't have a person do that, then the expert system is useless. As an example, if the doctor needed to do an x-ray and analyze something on the x-ray, expert system's really not going to help in that case. In fact, you're creating more work because the person's actually just going to have to do it by hand anyway. So there's no automation. So think about the automation component. Is it going to help you in terms of solving a problem in a more automated fashion? And the domain has to have a high payoff. You can spend a lot of time, for example, in your car as an example, you can spend a lot of time trying to figure out, you know, exactly how much gas is left when the light comes on. And write a really huge artificially intelligent program that will tell you every time the wheel moves how much gas is consumed. But you're not going to do that because there's no payoff to that. Instead, what you're going to do is going to illuminate a light and let the driver worry about it, because you're not going to break it down to minute little details like that. Also, you're not going to automate and create an expert system for something that doesn't really matter. You know, for example, grading systems, kind of rare. People aren't going to do automated grading systems. They're just going to do it manually. And plus, also, you have to also consider that, you know, the decision whether there is a payoff is in the eye of the beholder. So you can do, you know, profit kind of analysis, payoff analysis, and see if it's actually worth it. And the tasks do not require common sense. That's the other problem. If it requires common sense, How are you going to get a computer to actually possess common sense? Not going to work. So, how are they built? So the process is similar to rapid application prototyping, where you have an expert that is the customer, and the customer is basically going to want to put you in the computer. You're going to be the program. So you take the person and you try to say, well, what is it that you know? And capture all of their knowledge, represent it digitally, and then figure out how you're going to use it. And what task am I going to try and solve when I know all this information? So the experts involved throughout the development process, hopefully. And you have incremental systems that are presented that give experts for feedback and approval. You know, the expert can come in. If you are building a medical diagnostic system, you'd want to involve a couple of doctors to give their opinions. You know, are you properly diagnosing this using all of these prompts and all of this information? Is the database built correctly? Is there something we're forgetting in terms of the concept? And then the change is viewed as a healthy, not a process failure. In fact, you can take a bad system that doesn't work right and make it better by improving the knowledge, improving the inferences, the rules, and then all of a sudden what you end up with is a workable system that was fixed, which is actually kind of the interesting part about bugs in programs. People think, oh, program with a lot of bugs, oh, it's problematic, it's not worth anything. All you have to do is fix the bugs, and then all of a sudden the program is worth something, and it does do something. And actually, as a side comment, traditionally what's ended up happening in the field of artificial intelligence is people have built some of these classical systems, and it was for a different purpose. And then they figured out, oh, you know what, this works really well for that. And then they start using it for things they never thought that was actually good for, which is kind of interesting. We have different roles of different players in the build of expert systems and knowledge representation. One of them in particular is called the domain expert. So the domain expert is the customer, and it sounds like a very sophisticated word. We also have knowledge engineers who work in terms of engineering knowledge, creating knowledge, managing it. So the domain expert provides the knowledge and the processes needed to solve the problem. They're going to be the doctor. So in this particular case, the domain expert for a medical diagnostic system is the physician, is the doctor. The knowledge engineer is the person who's actually using it. So obtains the knowledge from the domain expert and uses it to implement the solution, maps the domain knowledge to the processes, and then AI formalizes, to allow a computation. So knowledge acquisition is sort of tricky. It's like garbage in, garbage out. If you come up with a bunch of bad knowledge, you've got a bad system. So we have bad doctors out there, actually. In fact, doctors who misdiagnose and kill people all the time. Usually they lose their license, but how many people are going to get killed before they lose their license? That's a good question. You don't want to take that person and represent his knowledge in your system. You also don't want to take a real good person's knowledge and then misrepresent it in a system and go, oh yeah, no, you got equal-I, when really you had something else or something. So it's kind of tricky. The expert must be available for hundreds of hours, and then the knowledge is in the expert system needs to be ends up being knowledge engineers' understanding of the domain, not the knowledge experts' understanding, because the doctor is not the computer scientist, nor is he the information systems specialist, nor is he designing the triage center. Somebody brought him in for a meeting and said, hey, what are the common symptoms of this? And he gave the common symptoms. And then someone else read it as, oh, you know what? It's Mr. Chow's. He can only get equal-I from Mr. Chow's. Oh. And then someone else comes in with equal-I symptoms, but they didn't eat it at Mr. Chow's. They ate at Mr. Cho's instead of Chow's. So they don't have it. And so it's the knowledge engineer's representation of the data that got messed up and not necessarily the domain experts. So it's kind of tricky. So we have different techniques in terms of acquiring the knowledge. As a description, we can have expert lectures or solve problem-solving tasks. This is where all the researchers come into place. They publish papers on this is the solution to this, and that's the solution to that, and that's how we're going to solve this problem. We can also do observations where the knowledge engineer watches the domain solve a problem and then mimics it. In fact, this is kind of common actually with manufacturing. So you can go into an assembly line plant and go, look at that. That person is stamping a label on a can. And then they actually, believe it or not, sometimes they build the robot to do the same thing. And the robot sits there with an arm and stamps the label on the cans. Here comes the can, the robot comes down, whoop, 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 like this. Redundant task all day. To replace That's an artificially intelligent robotics system that is replacing a human. It is an expert system. It knows how to stamp a label on a can. It's programmed like an expert system. It says if there's a label, put it on the can. And it's basically done in sort of a, actually it's kind of a cross between an agent, intelligent agent, because it's a robot agent, along with a expert system that's diagnosing, hopefully, or predicting situations. You may not necessarily need an expert system component with that. If the agent his goal in life is just to put a label on a can, no problem. But if there are no cans and you want to make effective use of this agent, if he has an expert system, it can say, hey, there's no more cans. Then the robot can self-propel itself and go over to the area where the cans are being created and then make cans. Change his job and make more cans or do something differently. I don't know, seal the cans, whatever happens to be the process. Then you've got an intelligent expert system that's designed that works with the robot. The expert system tells the robot what to do. So it's the person telling you what to do is the expert who is actually being mimicked by the program. Introspection can also be used in terms of interviewing, and after the fact you can interview to make sure that the knowledge is actually correct. Goal-directed knowledge engineering, find out what the goal is, what's going to be accomplished in each one of the steps, and document that as well. Some difficulties associated with this concept. It sounds all good and wow, everybody should do this, and this sounds like, you know, fantastic. So expert may not have the required knowledge in some areas. Actually, if you ask a foot doctor about stomach food poisoning, and you don't have any doctors who specialize with internal or whatever that happens to be the category, you're going to have a problem. You may also not be concisely aware of the required knowledge needed. So they might not, you know, you come in and say, hey, you know, you guys asked me in here and you're asking about this, but they don't realize you need knowledge about that too, which is actually kind of a problem in a lot of artificial intelligence. You forget, oh, the robot needs to talk or the robot needs to walk, but he also needs to jump, because what happens when there's a ledge? Oh, robot falls down. You know, so we don't necessarily know exactly until we actually try it out. And the expert may not be able to communicate to the knowledge engineer what the knowledge engineer needs to know, which is actually kind of a problem with a lot of the psychology programs. There's a lot of self-diagnostic psychology programs out there. In fact, some of them run off of the internet. You can go and you can say, you know, do you have this? Have you been to this region? You can type in a bunch of questions and it comes back and it gives you like 5 responses that comes back. The only problem is, how do you actually know that's accurate? Well, the problem is not with the information you're providing, the problem is with the communication. Meaning there's a piece of information that's not being asked, or there's a piece of information you want to give it, but you can't give it to it because it's constrained by the form of communication that it's working with. And then you get the problem of, well, there's no fact in the database that equals that, you know, and that there's no matching data that we can associate. So we have problems with communication. Also, knowledge engineer may not be able to structure the knowledge for entry into the knowledge database. So how do you put in this thing that doesn't fit the model of what it is you need to put in? It happens with databases all the time. When you go and you come in and you say, well, you know what? We need to update it. We need to add in the social security number, but it's the wrong format. You know, they don't have a U.S. social security number. They have a XYZ company social security number or something. Or you have a passport number, but you have a social security number field, and it's expecting a certain format. It can't get it, so you can't put it in the knowledge base. Instead, it gets thrown out, and then you go, well, and then the knowledge engineer doesn't realize that not everybody has a social security number, that some of those passport numbers are social security numbers and vice versa, and it's all messed up. Garbage in, garbage out doesn't make for a good plan. So we have phases that occur with knowledge acquisition, still on the topic of acquisition, acquiring the knowledge. So we have the initial phase. Scope of the problem. This is kind of like software in development, software engineering. In fact, looks very similar to a life cycle model, actually, where you have to identify the problem, identify the phases, you know, and then conceptualize. The key concepts of the operational and the page prototypes are built so we can figure out, you know, maybe a paper prototype. Something is built so that we can kind of envision what these problems are in terms of the identification. And then we can formulate a solution here. We have the formulation phase where we have a paper prototype and also a formal representation of the AI tools that are selected. Maybe some formalized report or something coming out of this. And then we have the implementation phase, where it's rewritten with using the AI tools. So we can actually kind of implement in terms of the tool set and implement the kind of problem solution that we needed. So we also have a testing phase that occurs at the end, and this is very much like a software development lifecycle model. It's following through, but it's kind of tailored towards a knowledge acquisition lifecycle. Knowledge has a life cycle, by the way. In fact, your knowledge has a life cycle, by the way, which is why you're in school right now, which is why you're taking classes. You're building your knowledge representation as a human. You're building your knowledge base. But some of the stuff you learned long time ago is not relevant anymore. In fact, some of the stuff you learned about computers a very long time ago, not relevant anymore. Instead, we have new stuff that comes up. If you've been a programmer for the last 20 years, your knowledge is old and worn out and broken. If you haven't been taking classes, which is why, especially when you're in a field such as a technology-related field, and you constantly find yourself having to update your skill set because your knowledge representation is completely out of date. It expires. Why? Because we have new languages, new platforms, new things coming up. Classic example, Windows 8. So if you're doing Visual Studio, you're doing .NET programming, you're doing anything right now, you got to go start take another class because everything that you've learned up to date is now obsolete because now we have a new platform out. Now we have a new way of doing stuff. That new way is going to overwrite the old way. If you don't learn the new way, you're out of a job essentially eventually. So same thing with Apple development, same thing with anything, even Java EE, changes constantly. So in the testing phase, you check both the classical test case and then the hard boundary cases. Terminology used to definitely separate out the type of testing that you're doing. And also, most likely problems are going to occur with I/O failures from the user interface problems, logical errors from bad rules, control strategy problems, and prototype revisions that might exist as well in terms of testing phases. Then we have the concept of truth maintenance, and I mentioned this already when I was talking about expert systems in the first part of this lecture. And the concept of there being bad data, and then truth maintenance, meaning is the data actually true? Because, for example, going back to the medical diagnostic system, Mr. Chow's could have had a problem in 2009, and I'm using Mr. Chow's as a generic Chinese name, by the way, because everybody's got Mr. Chow's everywhere. Hey, who knows? It doesn't really matter what state you're in or what world. Chow, for some strange reason, ends up being it's like Chow food. Ends up being the name of a Chinese restaurant somewhere. So somewhere in the world, Mr. Chow's had a problem, but that was 5 years ago. Now he retired and he closed his stores down, and then now we have another one. We have Mr. Cho's instead of Chow's. Or I don't know, you just change the name slightly. But then he's got a problem now, but he's not in the database. So the database is false. Because when you bring it up, it's never going to be a good match because it's not been updated, it's outdated. Now we have and this is called truth maintenance. We're still trying to make sure it's true. Or maybe Mr. Chow's got bought out by another person and he no longer has E. coli problems. He's got perfect, in fact, he's the best food chain out there right now. So we're not necessarily concerned with him, which means we have truth maintenance issues. We have to somehow figure out how are we going to update it to make Mr. Chow's now the best instead of the worst Chinese restaurant or something. So the task of maintaining the logical consistencies of the rules in the rule base. This is funny because this happens, believe it or not, in real life, and it happens, believe it or not, in the medical industry. When people think, oh, actually, you guys probably weren't here, but in the 1980s, they thought saccharin caused cancer. Actually, there's still people out there that think saccharin causes cancer. You know the diet sodas? Actually, they thought NutraSweet caused cancer too, So they put this in the database, and they used it as a symptom, and they said, if you've been drinking Diet Coke, as an example, or diet this or diet that, the artificial sweeteners, then you're highly likely going to have this problem. So the diagnostic systems kind of triggered off, and that was really bad information. But it was true at the time. Then they since went back and said, there's no linkage. There's no problem with that. Don't ask me if there is or not, because half the world thinks there is, half the world doesn't think there is. It's kind of like, do they really know what causes cancer? They don't know. So the hypothesis is there, this leads to this, that leads to this, right? And they keep changing their mind. So the truth maintenance, basically you need to incrementally go through and get rid of those inconsistencies. Only problem is, think about the internet. You can go online on the internet and search for a topic. Guarantee it, you can find, actually there's a bunch of myths out there. There's a bunch of false information out on the internet. You can find an answer to almost anything you want, and it can be the answer you want. In fact, you can search on the internet and say, is the earth round? And you can find examples where it's square, or it's a triangle, and it's not round. And you're wondering, well, what's true? What's false? And then the problem is you can't clean up the internet, which is why Wikipedia is bad. You go on Wikipedia and you say, you know, give me the definition of truth maintenance. It comes back and says, well, it's a matter of putting a Band-Aid on a problem, which is kind of true, actually. And then it comes back, no, it's when you have false information in the database, or everyone's got their own opinion on it, which is a problem with definitions of some words. You're never going to get the truth. So then you have all the philosophers that say, this is the truth. Yeah, okay, who knows really? Isn't truth in the eye of the beholder anyway? Because people are going to believe what they want to believe. Happens in science, happens in artificial intelligence, happens in knowledge databases. Your reality as a human is a different reality than somebody else's reality. Your truths are totally different based on your value sets and on your beliefs. So there's some basic laws of physics that people agree on, but past the laws of physics, we don't have any real truths in the world. So given the incremental manner in which rule bases are built, and since rules themselves are modular, their interaction is hard to predict. How do you know if you put precipitation in on your weather report, and then you put, I don't know, humidity in there, and then you put something else in there, that the inference that's drawn from the combination isn't something you would not ever expect? Which is kind of interesting, going back to what I was saying before. Sometimes people build these AI systems and they use them for things they never thought they were going to use them for, because the expert system is telling them something they never expected because of the relationships and the way that the connections are made between the rules, which just happens. In fact, there's a common test out there called the MMPI, Multiple Personality Inventory, actually. It's used as a career guidance test, actually. So it was originally designed back in the 70s, late 60s, early 70s, to diagnose multiple personalities. It was a psychological disorder test that psychologists came up with to say, we're going to figure out what your mental disease is. And they designed this big old test. It's been around for years. In fact, you can go online and probably take a version of it and have it tested. It's a really professional test, though. Actually, trained psychiatrists use it. They give it to patients. It comes back and says, hey, you have 2 personalities, or you have schizophrenia, or you have depression, or you have this. It was used originally for psychological conditions. Now high schools use it to figure out if you want to be a carpenter, a doctor, a police officer. They figured out, you know what, all this stuff is giving us different conclusions. It's giving us information we never thought was possible. And then they realized that, oh, this is career path information. Actually, you might want to use it for your CSLO essay now that I think about it. This is telling us that doctors in general have these traits. You know what the computer science traits are? You have strong logic connections, which is why you should like AI, actually. You should find AI to be an extremely easy course as a subject matter, which is funny because if I mention AI to any computer science, oh my God, that's really a hard class. Without them taking it, then they take it and they go, oh, this is like the easiest class I've ever taken, because it's logical connections. People who like computer science are also supposed to be good at math, and they're supposed to have a knack for math calculations, which is a good connection. So in high schools and in computer science programs and undergraduate levels, they say you have to take 2 semesters of calculus. If you can't get through, this is in the States, by the way, if you can't get through 2 semesters of calculus as an undergraduate student, you should not be a computer science major, because you lack the personality trait that's needed to be a good computer scientist. Doesn't necessarily mean because you're bad at math that you lack the trait, because then you go back to the diagnostic part of it and you go, well, what's wrong with this inference engine? Because I can't do math. Well, maybe you can't do math because you had someone telling you, I can't do math, I can't do math, which is what happens to girls, by the way. So women actually do better math than males in general. In fact, they're really better at artificial intelligence too, and they're really better at analytical skills. However, they're not nurtured that way. So that's why we don't have, this room is different because you guys are at a graduate level. You go to any undergraduate school in computer science, you look at the demographics of the room, I can tell you because I teach at different schools, 70-30, 70% boys, 30% girls, if you're lucky. Usually it's 80-20. A small percentage of the people sitting in the room will be of the female gender because they're told at a very young age that they can't do math. Or they're told that they can't do construction, they can't put blocks together to figure out logic problems until they go to school and they figure out, I can do that. And then they discover, which is why a lot of schools actually are trying to promote math programs to girls because they actually have better math skills than their than the boy counterparts because they think differently in terms of the logical connections, which makes you better organizers. So usually the gender stereotypes is the females are always the organizer. This is in America, so I don't know how different cultures are different, but you're the list maker, you're the organizer, you can keep things intact, you can keep the family unit together, and that's what you're trained to do. Well, those are analytical skills that computer science, so girls make better computer scientists actually because they have the background and the natural skill set from the nurturing from when they were young. Guys, on the other hand, I'm not going to get into whole gender roles here, but they also have better because they've been taught more. Their focus is on math and science when they're young, and they're told that they can do it versus told that they can't do it. So going back to nurture versus nature, if you're nurtured that you can do something, you're going to pick it up if you can do it. So the boys who get in computer science, the ones who think they can do it, usually, because they're not told otherwise. The girls have to figure out that they can do it before they do it, which is kind of interesting growth pattern. So there's been a lot of psychologists out there that have been like studying, and in the California school district, they've been like trying to, let's teach girls math, let's teach boys this, and they've been trying to like play around with the skill set to see, well, what works better? And the interesting thing is, and actually throughout my entire career, and in fact all the companies I've worked at, the women programmers have always been the better programmers. All the code is easier to read, it's easier to follow, it's more structured, there's a list to it, it's all organized correctly. The counterpart to that is sloppiness, unorganized, not controlled, but that's just a stereotype. It's not true, and I'm not saying that that's the case, but the male counterpart will have more education. They'll actually have taken calculus, they'll actually have the background for it, where the girls won't have the background for it. So they'll actually have a weaker skill set, but they'll have more talent. And then the male part has more talent because they have a stronger skill set on average. So anyway, it's just weird. In fact, going back to truth maintenance, it's because you weren't taught something, and I went on a tangent because I was talking about human knowledge bases. And it's combination. It's a combination of applying the rules along with nurturing the rules. And nurturing actually happens in artificial intelligence and in expert systems as well. So newly added rules can render old rules obsolete as well and can be inconsistent with existing rules. Just take society in general has different rules, for the longest time. Actually, I can tell you about, well, okay, another tangent, but this tangent is good. This tangent is good. So, actually, the last one was good too. The last one was kind of interesting, but 1950s in the state of California, I wasn't around, but my parents' generation was around. My mom never worked. She was a stay-at-home mom. She stood, she raised kids, right? And the expectation wasn't to go to college. So my mom never went to college, but my dad went to college. But anyway, long story short, if you have a kid today, expectation is that girl's going to college. Well, you girls are in college. You're not going to be a stay-at-home mom. How in the world is that going to happen? How are you going to afford to pay for anything? How are you going to live? You can't. It's impossible. So the old rule is now not the rule anymore. The new rule is the new rule. So then you have to adapt the other rules. Well, what are the other rules? Well, you have to sort of split the work at home a little bit more. I'm talking about the U.S., by the way. I have no idea how your families are working, and I have no idea how your culture differs. But in the U.S., when that expectation changed and when that rule changed, well, so did the rule about responsibility in terms of who's going to take care of the kids and who's going who's going to be able to drive and who's not going to be able to drive. Women never drove either, actually. In the 1950s, you never got a driver's license. You didn't need one. You never left the house, really. You just stayed home and did stuff and played with the kids all day. You didn't do anything. Now you have to get a driver's license. Now you got to go to college. Now you got to do all this other stuff, right? Because the rules changed. So the interesting thing is if you take a look at old movies, I can see it because I grew up in the States, and I know if you look at old American movies, whoa, cultural shock. It's like, wow, is this America? The expectations, the rule base is different. If you base a program off of that, you're going to get totally different results than if you base a program off of today. You look at that and go, and then even you can see it in vocabulary words. Certain words were okay 50 years ago, not okay today, because words have become derogatory, or words have become, not acceptable anymore. So you actually have to take that in consideration when you're building your knowledge base, which is interesting because the MMPI knowledge base has survived through multiple generations. It's the same exact knowledge base. It's the same exact test that was issued in the 1950s as is issued today. But the same rules apply. If you like math, you're good at computer science. If you like, actually law enforcement has authority issues. They pick, and it has military, so there's category law enforcement, military, actually judge is in that same category. All fits together with a certain type of skill set. Believe it or not, I'll tell you this because I can tell you from personal experience as well. Computer science and law is a good correlation between the two. So I'm studying law because I want to be a patent attorney one of these days, or intellectual property attorney. I'm actually a third year, but it's easy. But when I started, people were like going, "You're a computer science background. You don't have a law background." That thing is, and if you look at the MMPI and you look at some of the personality tests, it's the same person. The same person who's good at computer science is good at law because it's the same skill set. It's logic. It's taking the logical, it's math. Law is math. Computer science is math. It's all from the same line of logic thinking. Artificial intelligence is math. It's all the same thing. It's all kind of, so now you can know, well, for personality, if you figure out who you are, then you know what field to get into, then you know what field to get into next and next and next, so you can kind of move around and not have to do the same thing for your entire life. So you might consider law, actually, because you guys are, if you're computer science people, you're going to love law. It works, actually, which is actually, believe it or not, the current trend. A lot of burnt out computer science people are studying law, so they become intellectual property attorneys, because you can go and work at Google. There's, I don't know, maybe about in the area of about 500 local Bay Area lawyers who work at Google, who prosecute or who do things with patents, and file things and working with copyright infringements and patent infringements. And this algorithm is the same as that algorithm over there. Your technique is the same, likeness comparisons. All this stuff is actually kind of a nice transition for people that are tired of programming, people who are tired of working in computer science. So how are you going to maintain this truth in this database, and how are you going to keep the knowledge up to date? Well, you can hand check it. Not so good. Or you can use some formalized way of examining the relationship among the rules and see if it's still true. So you can put together decision trees, truth trees, inference trees, run some data through the trees, and see if it's right. As an example, the whole formula of the, any of those problem scenarios I was giving you a few minutes ago, you're going to just put all the stuff in there and say, is that right? No, you're living in the 1950s, that's wrong. So then you can go, oh, this decision is right, this decision is wrong, kind of thing. Causal models also exist, so do automated tools. So there's a lot of, these are the research areas where people have formulated tools to develop techniques for testing the truth values of the inference engine and of the knowledge base, which is kind of interesting because textbooks are like that as well. So some textbooks are just out of date, get rid of them. And then other textbooks have been around since the 1950s or 40s or so, and they're still relevant. It still works, but you don't know until you test it. That's usually a manual testing kind of thing. There's an inference net that shows the rule interactions, and you can look at the rule interactions and see if the outcomes are correct. And I think something that actually went over in terms of an update and a modification was the credit reporting system, and it happened about 5 or 6 years ago or so, Well, we had to change the rules around a little bit because people don't stay on their jobs forever. So, which is actually kind of interesting because if you go into cultures like Japan, people work at one company their entire career. They never switch companies. So, how is it where you guys are from? Actually, it's kind of an interesting question. You guys, is the expectation you're working one job for your entire life at one company? It can't be. It can't be the same. No, it's not the same. It used to be like that in the States, actually, and you moved up in your career. So if you're not educated, you have a mindset of the 1950s, which a lot of older people actually still do. You get in on a job, and they hired you when you were 19 years old or 20 years old, and now you're 40 or something, 20 years later, and you're still in the same job, and you're still working the same position, and you haven't been promoted yet. That's a red flag right there. But you're waiting to be promoted because your father or your ancestor right before you, that's what happened to them. They just get a job and then they get promoted throughout the years, and by the time they retire, they're supposed to be CEO of the company or something. That doesn't happen anymore. It used to happen though. It still happens in Japan from what I hear, actually. You get this low-end job, you stay on the job. The longer you stay on the job, you work through the ranks. No longer the case anymore. But now in order to get promoted, you leave the company and you join another company. But that's based on a very, very old inference engine. It's no longer valid. That's just one example. I can come up with like thousands of examples where things have changed, no longer valid. Like how many cars should a person own, or how many pairs of shoes should a person own, or what should a person study in school to get somewhere? Totally different. Changes every year. Purpose of the explanation system and why you want to put one together is not to teach people how to cheat your system, because that's what people do. Actually, people do that with the job market. They go, how more am I going to get away right now without going to college? I'll take a mobile app certificate program. That actually works. You can make more than someone who's got a master's degree if you take the right classes and you get the right job. Without a college degree, without even an undergraduate degree, you can probably make about 120 to 135 or so thousand a year without a college bachelor's degree by knowing the right stuff right now for what's needed in the job force. And I'm talking about app development jobs, actually, which actually know a couple people with high school diplomas, no college at all, who are making more than I'm making. So doing less work than I'm doing. And you think, oh, I'm jealous. Why did I do that? Well, my inference engine didn't work correctly. I got into teaching instead. Teaching's like the lowest paid career out there. But I don't do it because of my inference engine. Well, my inference engine is old and outdated, and I haven't updated it yet because I should be doing app development right now. But I'm breaking the rules. I know the explanation of the purposes of why I did decisions, and I'm looking at the purpose of the explanation. I know that. I just don't agree with it. Because I'm human, I can kind of say, you know what, throw it out the window. I know I should be doing this, I'm not doing this. Because people do what they like to do all the time. It doesn't have to be the logical decision. So I'm not making logically correct decisions with my career path. However, I can kind of justify that from a human perspective. So your artificial intelligence system can also justify by providing an explanation for why it made a choice a certain way, and then you can use the explanation to improve the artificial intelligence expert system, or to explain to the users of the system why it decided a certain way. So assisting in the debugging of the system also informs the user about current system status. Well, the current system is working on values that were a long time ago. It's not working on today's value. Increase user confidence in the advice given by the expert system. So that's one of the reasons why this MMPI actual exam is, it's been around since the 1950s or so, or 60s. It's been around many, many years. People have confidence in it. Just like the SAT scores, people still have confidence in SAT scores, standardized aptitude tests that high school students take to get into colleges, and you take the GMAT or the GRE if you're in the United States. And people have confidence in that. It's a system. It works. They don't like the system. They always complain about the system. But you learn how to make the system work for you. Then you take a GMAT course. Your likelihood of getting a better score goes up by 20%, I don't know, things happen. So it helps, actually, the feedback from the system helps explain the system, clarification of the system terms, the concepts, the help that's provided as part of the system design, and also increasing the user's perspective, expertise. So user's personal expertise of tutorial. So increases the likelihood that they're going to actually be able to use the system more productively. Here are explanations that are in an N or tree type of explanation. So a person needs to eat, and they don't have any money, so they can steal food. Okay, that's a good option. Doesn't lead to anything, though. Doesn't go anywhere. Or they can earn money, and then they can write a book or find a job, or they can consult in an agency and prepare a resume and get a better job or something. Or they could borrow money and go to the bank, or find security somehow, or make an appointment, do all sorts of, all these decisions are made are explanations. So a lot of researchers who put together, and this is what you get when you do the MMPI or do some of the other standardized tests that are out there, although the SAT doesn't do this for you. It gives you scores in certain areas and tells you how the main score was built up. But it doesn't give you explanations of the formation of the conclusion that it makes. So other programs will, and the explanation will help you figure out more information about the problem than a simple yes or no, fail or pass or fail that comes out of it. So the explanation mechanism, we have why questions answered by considering the predecessor nodes of all of the given nodes that lead to a final node, considering sub-nodes that might go, or sub-goals that are associated with nodes. How questions that are answered by considering the nodes themselves for a given goal as well. So how or why questions. Also the reasoning system. A lot of people publish the reasoning systems because it gives you kind of the ability to see how the conclusion was derived. So we have the retrospective reasoning, how or why explanations, and we have the counterfactual reasoning, the why not capabilities. Why not do it? Why did you not select that option? Or the hypothetical what if compatibilities. What if I do this? What if I do that? What if I don't do this? Which are kind of the reasoning systems. And then we have the causal models that work with this. You can provide expert system designers with the information needed. Causal models might be an observation, and causal model might be, well, this test that you've got that is working for psychological disorders, it does a really good job determining proper career paths, because it actually accurately described the person and said, hey, you must be you must be a construction worker. And lo and behold, the person was a construction worker. Or you must be a police officer. And it comes back, yeah, I'm a police officer. And it basically diagnoses professions correctly, and you're like, well, how did that do that? Well, by your psychological personality that leads to diseases. Well, it also determines what you're good at in terms of professions and level of education. In fact, they can determine the level of education from a person by an expert system, which is what they're trying to do with comprehensive exams. So if you go to this university doesn't have it, but if you go to a master's program at other universities, they have this thing called the comprehensive exam. You're supposed to pass the comprehensive exam. If you can't pass the comprehensive exam, that means you don't have a graduate level education. Comprehensive exam, people stress about that, but everybody passes it because it's the minimum level you need to prove that you're competent enough so we can stamp master's degree on you or a PhD degree on you. And if you go to a PhD program, you have to take a comprehensive exam and you have to write a dissertation because they want to make sure when they put the label on you that you actually meet the psychological and the mental capacity as well as the intellectual capacity to be labeled this way. Otherwise, the university is going to look funny. You're going to say, oh, well, this PhD person is working at McDonald's because that's the only job skills that they have because they graduated from your school. And, well, we've taught them how to flip burgers. Not to say that because they work at McDonald's, the school is bad. But they want to know, in that particular case, probably the guy got into a car accident maybe and hit his head, broke a few things, so that's why his only job he can get is work at McDonald's. Maybe that's the explanation for why he's working at McDonald's. Not to say that if you work at McDonald's it's a bad job. I'm just saying if you've gone to MIT and you've graduated, with a PhD or something like that, maybe you shouldn't be working at McDonald's. Maybe you should be doing something else. Who knows? So that's the kind of the old way of thinking, however, because now people go to college and they get degrees for different reasons, not necessarily because they want to work at, a good company or something. They're getting it for different reasons usually. So, all right. Actually, not to go on a tangent again, but American people usually go to college out of expectation. And some of them study stuff they don't even want to do because their father was a lawyer and their father was a lawyer and their father was a lawyer, so they have to go to law school. Law schools are full of people that don't want to be there. Medical schools are full of people who, oh, my dad was a doctor and his dad was a doctor and his dad. This is an American thing, so they have to do this. The military is full of people who don't want to be in the military. It's because they're the son of someone who was in the military, and their father was in the military, and their father. And then people who run family businesses who don't like, they have a bakery, but they hate food, or they hate bakeries, or they run a deli, but, it's because they're not there because they want to be there. And those people are terrible. Some of those people are really bad at what they're doing, but they're there. So this is not a career counseling course, but telling you, if you like what you do, you're usually better at it because your personality is leaning you in that direction versus making the decision. And this is relevant to expert systems. If an expert system tells you you're supposed to do something, you usually want to know why. Are you telling me I need to do this? Because maybe you don't agree with it. And if the expert system says, well, we base that rule off the fact that your father did this or your mother did this, and this is what you're supposed to be doing now, well, the rule may not apply. So the inference engine is wrong, and the data is outdated. So you got bad information in there, and it's bad. So here's some more causal model links, cause and effect links. And so the causal model is actually theoretical based in terms of associations. There is a cause and effect link. We have a broken belt with an engine problem, perhaps, or an effect cause. A car won't start. Well, we might have a problem that's affected by the engine. Or the definitional is a inheritance. The fuel pump is a problem. Well, we have a fuel problem that's associated with the fuel pump. These are associations that are made with causal links in terms of the model of the data. Or the association where there's a related fault with no causality, or there's no cause for the fault. There's an internal problem. Well, we don't know what the problem is. It's probably a cooling problem or something. So we can take a look at the problem of a car not starting. And we can say the car won't start. Well, it could be a fuel problem, could be an electrical problem. I don't know, it could be that there's no engine in the car. Someone stole the engine or something, which is kind of an interesting problem. No spark plugs, perhaps, no fuel pump. So we can actually map out the problem solution and look at it, and we can say this is the casual way of kind of figuring out, which is what people do. When you need to make a decision on something, I guarantee it, nobody in this room maps out a network of all the possible ways that the decision could be made, follow the paths to see which one's going to lead to the best goal. Probably not. Instead, you're going to flip a coin. You're going to use a causal model. You're going to go, well, if I do this, I'm going to get that. If I do this, I'm going to do that. If I show up to class today for my ITU AI class, if I show up today versus not showing up, you're trying to make that decision. If I show up, I might actually find out what's going to be on the final exam. Or maybe I'll even get attendance credit. If I don't show up, well, I run the risk of them giving me an F in the course. But hey, they didn't give me an F the last time, so maybe they're not going to give me an F this time. It's a casual way of deciding whether or not you're going to show up. Explanation of problems. Rule-based problems are composed or compiled knowledge. So the domain is dependent on the reasoning. So it's removed when the rules are created. So in fact, the reasoning can change. So the rules give you the reasoning. So if all people who don't show up on Fridays for the AI class get failing grades, and that's the rule, and then you apply the reasoning to it, it doesn't match. Well, maybe the person was stuck. Maybe their plane didn't show up. Maybe the reasoning behind it wasn't that they didn't want to show up, perhaps. Maybe some of them didn't want to show up. But it has nothing to do with reasoning. It's a rule, which is weird, because you have to play the rule. If you're a student and you're not wanting to get an F in the course from failing attendance purposes, the reasoning is going to be totally different than the outcome of the rule. As an example, there were some people that, naturally, everyone's going to have problems uploading into the EMS. But if the reasoning is that you waited until the minute before midnight and then you forgot, it's different than if you just didn't do the assignment completely. The rule is if it doesn't end up there by midnight, you don't get credit for it. So the rule says the rule. So if you enforce the rules, which what we're supposed to do actually, and you don't apply any reasoning to it, then anyone who didn't put anything in by midnight gets an F, or gets a 0 points for it. But if the reasoning is, I got stuck at work and I forgot, or the EMS failed and it wouldn't take my assignment, and it wasn't really your fault, it was the system fault, then if you're just going on the rule-based system and following the expert system, you get a 0. And then the reasoning part of it says, let's break the rules, which is what humans do. And the point of bringing up this is if I weren't a human, if I were an expert system, there's no breaking of the rules. It's pass or fail, it's in or not in, which is a problem with expert systems and automation. So here's the problem you're going to run into, and this is a valid problem that you're going to have next term. If and when they put that Turnitin.com in, and I'm actually kind of glad it's not in there right now. I don't think it's in there. At least I'm hoping it's not in there. Because here's the problem. Right now, humans look at it, and humans can see abnormalities. They can see when 5 assignments match. They can see it. Put an expert system in there. Turnitin.com is an expert system. Is a great example of an expert system because it's going to look at your paper. There's no human involved. It's rolling on rules. It's going to say, does it match? Does it match? Does it match? Maybe you turned the paper in before. Maybe the paper's already in the database because you decided to recycle a CSLO, as an example, and the rule says can't match anything. So it comes back and gives you a 0. Or maybe it gives you a percentage, because the 0 is going to be based on a percentage of plagiarism that is found in the paper, which is how Turnitin.com works. So somewhere in this expert system it's going to determine that, hey, if you turn in a paper that's more than 50%, I'm just using this as an example. I have no idea what the rules are going to be. Someone's got to build a rule set in there that says if the paper has more than 50% plagiarism and the student's going to get a 0, it's going to show a 0, then it's going to send a report to the student, send a report to the instructor, and it's done. You know what kind of problem that, this is why I say, I hope it's not implemented. You know how many problems that's going to cause? Because what if the reasoning was, you turned it in to check the paper? I'm not saying that this is going to be the case, but let's just say, for example, you submitted it to turn it in before you turned it in to check it, and the system didn't clear it out. So now it thinks it's a repeat, and it's a mistake that the system made, and the technology of the expert system saying, it's more than 50%, it's 100% match, because there's a paper in there already, because you turned it in to go check it out. There's no reasoning. There's no breaking of the rule. There's no modification. It's going on a strict rule base. One of the faults of expert systems doesn't know how to reason. It doesn't know that, oh, I checked it last night and then I turned it in today and it came back 0. This is not going to happen to you, I hope. But the thought has crossed my mind that can you just take a number and put a score on it that's coming from the system? It'll be interesting. Maybe some of you guys will graduate, you won't have to experience this, but it'll be interesting to see how that automation sort of works. I suspect there's going to be some bugs in this system. No expert system is definitely going to do it. So what everyone's recommending is don't put a 0, just put the percentage out there. And so the percentage is a red flag, which means you're getting information, you're getting an explanation that's coming back out of the system, and it's going to be no 0, but maybe a percentage that says 70. 70? And then you can go look at the paper and do some reasoning on the paper and go, you know what? This is unique. There's nothing wrong with this. And then you can override the rule. What they should not do is put 0, 0, 0, 0, because who's going to look at it? You got a 0, you got a 0. You plagiarized. But I didn't plagiarize. How do you know? Well, if no human's looking at it, you can't tell. So it'll be interesting. I'm not trying to scare you, but take a look. Don't trust what you see, because most likely, if they it depends on how much automation they apply. I have yet to see the feature implemented yet. However, it's on the agenda, it's going to be implemented, but it's a way of doing an expert system using a plagiarism checker to see if the assignments you're turning in are correct, or are they plagiarized. So it's doing a determination based on a rule set. The rule set's coming from information that's coming from another expert system that's coming back and saying that 60% of your paper is plagiarized. Well, it's because I forgot to reference a source, or is it because of this, because of that? It doesn't tell you, it just comes back with a percentage, but there is data in there. So hopefully that data will be saved and the data will be sent to you so you know what's wrong with the paper. It should. It should. I'm sure there's ways, in fact, if you go online, you can find there's ways of cheating the system. Because it is an expert system, there's ways of figuring out the feedback from the expert system. It's all over the place because almost a lot of schools use Turnitin.com, and there's ways of cheating the system, and it tells you how to do it. There's websites that tell you how to cheat the system, actually. Not promoting that. I'm not saying you should do that, but when you start looking at the cheating, and I actually did that, and then I went, oh, wait a minute, then. So it tells you don't turn it in before you turn it in, and wait a day or something because the system needs to refresh. And if the system hasn't refreshed, then it's going to come back and tell you that it already exists. It's 100% plagiarized because you turned it in. It's already in the database, but it hasn't refreshed it yet because when you canceled it, it didn't cancel correctly or something. And then there's different tricks with quotation marks and stuff like that where it could be properly referenced, but it doesn't match identically. The year or the dates doesn't match identically to the reference, so then it comes back plagiarized. There's a whole list of stuff it's an expert system, so there's a whole list of ways of beating the expert system and then also working with the expert system. So I'm pretty sure they're going to publish something or make it available to you guys to tell you what the rules are, to say that, you know, this is why it's coming back a certain way and here's how you do it so you don't have that problem. So maybe you guys will be around. You're probably going to be graduated by the time this thing is actually implemented. I seriously think it's going to take a couple of years before it actually gets implemented. It's tricky. You can't just put it in. If you put it in, you know, there's likelihood of it making a mistake. Because you really want it to make a mistake. And if you do put it in with that likelihood, if it gets put in, it won't be automatic. It'll just show the score. And the teacher will put the score in there. So. It does actually work, and what I've been talking about does explain and have explanations of problems, so it's relevant. The little tangent that I just went on actually is relevant to the slide you've been looking at. Rule bases are composed of compiled knowledge. Compiled knowledge is what I just described to you. Knowledge of what makes the system work correctly, what makes it work incorrectly, and the domain that's dependent reasoning is then removed when the rules are created. So there is no dependent. The reasoning changes sometimes when the rules get put in, and expert systems relies on the use of the domain independent inference strategies. One rule set that applies towards one set of rules might be completely different, or one scenario might be completely different than rules that apply towards something else. The weather system is actually an interesting example of that. Precipitation might tell us about the likelihood of rain. Not going to tell us about fog. Not going to tell us about dryness. Not going to tell us about, you know, weird things that happen. So, which is kind of interesting. So, they can look at weather patterns, and you know, last week kind of violated a lot of the weather patterns that we've seen over the last 50 years or so. So, a lot of the weather programs put up these little alerts and said, "Hey, there's a violation in all of these rules. We have abnormal weather." And then they were calling it earthquake weather for a while. No longer earthquake weather, and they changed their minds on that because the inference engine came back with different rule sets. Now it's just normal. Now we're normal again. So I'm going to end this video because I'm going to switch the topics on us. So let me end this video here. That one was on